guys, how you doing? Today we are going to be talking about graphing, speed, and force.
We're going to be using our roller coasters and ramp set, and so today we're getting out our cars and our ramps. We are super bummed that we cannot be in the classroom with you guys today.
You guys have no idea how much we wish we could be in the room with you guys doing this. It is so much fun. It's so hands-on, but this is the best that we can do right now to show you how awesome this stuff actually is.
So keep a hold on the video. We're going to kind of stop it and start it as we go through, so please pause it and go to your document. If you follow along with us, today should go well.
Awesome. Part one, we're going to look at these three different graphs and looking at the position versus the time. So if we look at this one, we can see that we have a curved line, but it's going in the positive direction. So with this curved line, all that means is his speed isn't constant. He's not moving at a constant rate, but he is always moving. His line is never flat. So even though we may change speeds and change our rate at certain times during that graph, we're still moving in a positive direction. So we're still increasing our position, increasing our distance. In this middle one, we have a flat line for our position versus time graph. And that means that his position is staying the same over this entire graph. Over all the time, he's not moving his position. It is constantly at this spot. So he is staying the same in that spot, or in that graph. And then in this last one, we have a positive line moving in the positive direction. It is completely straight, so his rate is staying constant throughout that whole graph, so he's constantly moving and increasing his position.
Go.
For the second graph on here, we're going to be looking at this position versus time graph and all of these different 4 numbers. So looking at here, we just need to, using the graph above, rank the 4 positions in order from slowest to fastest. So by looking at this, we can see at this spot right here, he's not moving. And remember up at those 3 graphs, we said when that line is flat on a position versus time graph, his position is not changing. So he's staying the same, staying at the same spot, he's not moving. When we go from here to here, you can see that that line is a very, very gradual increase. So he's moving very slowly. His position is changing, not very much over a long period of time. But then when you look at number 2 over here, his position is changing drastically over a very short period of time. So that means he's moving very quickly.
Alright guys, so we are officially going to start our cars and ramps. We're super bummed that we're not in the classroom with you so you could do this with us, but we thought it'd be best to just kind of show you, give you an idea of what we would do in the classroom, and then go through the doc with you. So here is our ramp. These are called photo gates. This is our photo gate B. So as we read through here, it says refer to the picture. So this is kind of giving you the general idea of what this is. And then this is obviously our model. It says they are calculating the speed of the car at different locations on the ramp. So here's our car and our ramp. So this is our timer. This is going to kind of track how fast it goes from A to B. These are called photo gates. These actually come off, and we have a ruler here on our ramp that we're able to kind of track and measure how far apart our photo gates are. So this is A and the red is B. And so if you notice on the graph, our table of charts here, it says our photo gate B, which is the red one, is going to be 20 centimeters away from photo gate A. Then we're going to test it at 30, 40, 50 as it goes down. So we'll be moving our photo gate down the ramp as we go. So when I let go of the car, there's a black chip on the car, and that kind of activates our photo gate to start and our photo gate to end. So it'll start the timer, end the timer when it goes through. And we are calculating the speed in this part of our lab. We're calculating the speed of how fast it took to get from A to B. So our chart here is showing you that it took 0.129 seconds to get from A to B. And then when we moved this down to 30, it took 0.225 centimeters. So we already did the graph and data for you, and so now we're kind of moving on. So step 3 here says, using these numbers, you're going to take this chart and graph the information, and just like we did in the beginning, you're going to go to Google Sheets and you're going to create your own graph for our data.
now that you guys have done your graphing, we're going to move on to calculating the average speed. So question 4 says, calculate the average speed of the car that traveled 80 centimeters from the graph of your data. Make sure to include the units. So you're going to look back up here, and all of this information is in your graph too. You have the position of the photo gate, that is our distance. And then you have the time from photo gate A to B. So this is the time that it took that car to move from one spot to another. So you're going to take your distance and you're going to divide it by your time. So you're looking just at this last row here, distance divided by time, to find your average speed. Okay, so then we're going to scroll down to question number 5, and you are going to have to keep that speed in mind that you found up there, because now we need to calculate time. So it says, how long would it take the car to travel a distance of 200 centimeters at this average speed? So we're going to rework this speed equation into solving for time. So now it's the equation that you're going to be using is time equals distance divided by speed. We're giving you your distance, which is 200 centimeters, and your speed is what you calculated up here. So you're going to do distance divided by speed to find your time for this one. So similar to the other equation, we're just kind of rearranging it a little bit. And then number 6, make a final conclusion about the data and graph above. What happens to the car's speed as it travels down the ramp? So going back to this data, what do you notice in this column? What happens to the car's speed as it goes down the ramp? Now remember, this is just the time that it's taking it. In order to find our speed, we have to go distance divided by time. So what do you notice about that? Just kind of draw your own conclusions and put it in your own words.
Heading into part 2 now of our cars and ramps unit, and we are going to focus on force. And so force is a push-pull. So if you follow along with me on the document, it says it is an action that has the ability to change motion. Force is needed to start an object moving or to change an object's motion if it is already moving. So forces can also change an object's speed or change the object's direction of its motion. So what we're going to do today is we're going to change the ramp steepness. And so if you notice on the pole here, there's holes. And so if we count from the bottom, here's 1, 2, 3, 4, 5, 6, 7. We are at notch 8. And so when this says the hole where ramp connects, we're talking about these holes and how this kind of gets moved up and down. So I'm at 8 here. I'm going to take my spring scale and I'm going to attach it to my car here at the front. And as I pull it back, we'll be able to see how much force is being pulled down to pull the car down. And so if you notice here on the picture, it shows you your spring scale, and it shows you your car, and it shows you your ramp. Right now, we're not going to worry about the weight, so disregard that on the picture. But we are kind of pulling the car up the ramp. And when we do that, we'll get different numbers as we pull it at different inclines. And so right now, we are at notch 8, and when I did pull my car up, I did get 2.9, and remember, we're measuring in newtons for the force.
As you can see on this document, we gave you guys the graph this time. You're welcome. So it says the relationship between the hole where the ramp connects and the force. So if you look down here at the bottom, our independent variable is the hole on the ramp. So that was changing our incline. That's what we changed. That's what we manipulated. So that is our independent variable. That's on the x-axis like this. So hole where the ramp connects, independent variable. Dependent variable is our force, because as we pulled that car up the ramp, we were measuring the force in newtons. So dependent variable on the y-axis is force. So you can see this data here on our graph, and you guys are going to have a couple questions to answer about that. So the first one is, what is the relationship between the force and the steepness of the ramp? Fill in the blank with the words increase or decrease. So you are going to fill in the blank with, as the angle blank increases or decreases, the force blank. So you're going to look here. The higher up the number is for the hole, the higher the increase is. The higher the incline is. And then you are going to look to see how that affects the force. Okay, so that is the first question. This is going to lead into a discussion of inverse and direct relationships, but that is coming into the next lesson, so stay tuned for that one. And then number 2, suppose you're pushing your friend in a wheelchair up a ramp. Which ramp should you use if you want to use the smallest force? So you don't want a whole lot of force here. What ramp, A, B, C, or D, do you think you should push your friend in the wheelchair up, and then tell us why? For the wheelchair question, this is just an example for you guys. A would look something like this. This would be the steepness of that ramp that you would be pushing your friend up. And D would look something more like this that you would be pushing your friend up. So decide which one you think would be best to use the least amount of force.
Wow, you can really dance. Wow, you can really dance. He went. They said we've both been dancing all this time. What a coincidence. Wow, you can really dance. Wow, you can really dance. He went. They said we've both been dancing all this time. What a coincidence.